So I'll start with a little diagram here. We're going to have a vertical spring, and there's a mass hooked onto the end of it, and this is bobbing up and down. It will bob up and down. And we're given some specific moment in time here. I'll call that moment 1. Okay, I'll call that moment 1. So all my subscripts will be 1, referring to this moment. So part A, calculate the total mechanical energy at this moment. Now I'm given the mass of the object, 200 grams, which needs to be changed to kilograms for SI units. We're given the spring constant, 8 newtons per meter. That's not too strong, but okay. We're given the speed at this specific moment. I'll call that V1, 2 meters per second. And we're given that the spring is stretched, so I'll call that X1, by 10 centimeters, which again, I need to convert that to SI units, so 0.100 meters. Those are the values I'm given for moment 1, and that's going to be enough to calculate the mechanical energy, sort of. What we're not given is how high it is, so what we can do is choose a reference height. Okay, choose whatever reference height we want. So in this case, I'm just going to choose where it is right now, wherever it is at moment 1, that's going to be the reference height. And if I choose that reference height, then my mechanical energy, my gravitational potential energy, will be 0. So U gravitational and U spring, the gravitational one will be 0 due to the choice of the reference height. The other two I can just calculate and add together. Those are the formulas for the energies. Sub in the values. The SI values and figure that out. All right. Yeah, let's go with the mental math here. So half times 2 squared is 2 times 0.2 is 0.4. So I got 0.4 plus half times 8 is 4. 4 times 0.1 is also 0.4. So in total, that'll be 0.8. It's going to go it'll actually go to 2 decimal places if I do it properly. Okay, so that's the answer. That'll be in joules. That's the answer to part A, the total mechanical energy at moment 1. Part B, so now we're going to get to a different moment. We'll call that moment 2. I'm just going to switch colors here for moment 2. And just hit green. So that's just my legend here. Moment 2, I'm using green. So it says now it's only stretched by 5 centimeters. So it's going to be a shorter spring by 5 centimeters. Meaning the object has risen by 5 centimeters as well. So the difference between the reference level and this new height is 5 centimeters. Yeah, because the spring was 10 centimeters stretched originally. Now it's only 5 centimeters stretched. That means this object has actually been pulled up by 5 centimeters. Okay, now determine the speed. So determine the V2 of the object at the new moment. So this is a conservation of mechanical energy question. There's only gravity and the elastic force here. Both of those are conservative forces. So we can conserve mechanical energy. So that looks like ME1. I'm going to just write ME1 because I've calculated that in part A, 0.80 joules, and that's going to equal to ME2. Mechanical energy is conserved. ME1 equals to the sum of the kinetic and potential energy at moment 2. That's what mechanical energy is, the sum of kinetic and potential. And unfortunately, I don't feel like we have any zeros here, so we're just going to have to suck it up and write all the formulas out. And that's going to be solved for V. That's going to be solved for V eventually. What I'm going to do is I'm going to fill in the values a little bit earlier than I might normally do. So 0.8 joules is on the left side. I'll keep half mv squared in variables, but mgh, I'm just going to kind of calculate that, get the number, and just plug in that final value. So the height at moment 2, it rose by 5 centimeters. So the height would be 0.05 for SI units. So this turns out to be 0.098 joules. And the K2, I'm just going to calculate that off to the side as well. Oh no, sorry, not kinetic, spring. So the stretch is 0.05 meters squared. So that gives me 0.01 joules. So oh, there is a mistake here. Okay, sorry, I gotta go back. Because those numbers seemed really small compared to 0.8. So now I'm realizing that going back to the calculation, I forgot a squared here for the kx squared. So gotta fix some of that. So this is going to be 0.04 actually. So this will add up to 0.44. And that's the new number. Okay, so I'll go from there. I'm going to try to isolate for V2. So I presume I'll start by subtracting the 0.98 and the 0.01 from the other side. Giving me 0.332. And then I will multiply, well, let's do it all at once here. So I'll multiply by 2, divide by the mass, square root the whole thing. The mass, I can substitute 0.200 in there and calculate that out. Leaving me with 1.8 meters per second. All right.